Okay, so since this is the last day in my final lecture, I just wanted to thank the organizers again for this great conference, and I really enjoyed it. I'm sure the people did it at the very end. Oh, does it work? Oh, maybe I put it too low.
Just talk about it.
Just talk louder. Well, sometimes it was making terrible sounds. But anyway, it's really been a pleasure to be here. Thank you guys for organizing this. It's wonderful. So for the last lecture today, I'm going to talk about some aspects of sort of what does quantum gravity look like from the point of view of an observer inside the bulk, and that will connect to a variety of ideas, such as traversable wormholes and some other aspects of bulk reconstruction. And I think this question is, I think, especially an important one, given the fact that we live in de Sitter space, or a space-time that's similar to de Sitter space, and that it doesn't have a time-like boundary at infinity, or even an asymptotically null boundary.
We're not sure of that.
Could be. Well, could there really be a time-like boundary at infinity?
Well,
Maybe in principle, very far away.
Decays.
Oh, if it decays, no, but even then, it will be like null in the future, right?
Yeah.
Yeah. It will be
Could
null
be
in the future.
asymptotically flat in the future.
Could be asymptotically flat in the future, but it's still different than the setup which is asymptotically flat with both the past and the future with an S metric. So. But in any case, especially in a universe like ours, also we live in the bulk. Okay, we are not asymptotic observers, at infinity. There probably isn't an infinity where there could be such an observer, but even if there was, we are not that observer, and so it seems important to understand something about what does it look like when you're inside of the space-time, and so. As far as we usually think about the things like the black hole information problem, we'll often formulate them from the outside. So we think about it as, for a flat space, some scattering problem. We send in a shell of stuff, it collapses into a black hole, eventually it evaporates, and how do we see unitarity of this evaporation, and even how do we see it in the gravity theory, and that was related to these issues like the overcounting of states by the semi-classical theory, and maybe our universe is described by, say, string theory, which is a consistent theory, and at the end of the day, it all works in some way similar to what I alluded to, say, in the third lecture, where when you actually count everything, there is no overcounting the states, and it's all unitary. So that's what we imagine happens, but still it seems to not completely answer the question of what is the experience of somebody who jumps into the black hole. Right? And there are, of course, some things that we believe to be true in these contexts, which sometimes we take for granted, but they have somewhat surprising consequences from the point of view of an observer in the bulk. And one of the most basic ones is this idea that entangled states are dual to connected wormholes. It sounds innocent at first, right? I mean, even if we look at the most classic example of just a thermal field double state being related, thermal field double state and two copies of this holographic CFT. So here's a CFT left, here's a CFT right, and we have the TFD state at some temperature. We associate this to the eternal two-sided asymptotically ADS black hole. But this is already a little bit surprising, because if we look at any factorized state, suppose we looked at a state, not the TFT state, but a state in the same Hilbert space. So the Hilbert space here, from the CFT side, is just a product, because the two CFTs are in two different universes, two different spaces, and have nothing to do with each other. And then we consider this entangled state and draw this picture. But on the other hand, in the same Hilbert space, if we were to take a factorized state like this, well, in this situation, we have two CFTs with no interaction and no correlation and no entanglement. They just have absolutely nothing to do with each other. I mean, we could be living in the left CFT, and this could be a figment of our imagination, right? It doesn't say anything. And so, of course, the dual that we would associate to this kind of state seems clearly to be one where there's some kind, maybe these are typical high energy states. So the dual will be some kind of black hole microstate in that sense. Need not be an energy eigenstate, but
Operators from left don't necessarily always commute with operators on right. So,
what do you mean?
I mean, if you take something from left, throw it inside, across the horizon, then you can take an operator in right.
You mean in this space-time? Well, first of all, the operators of the left CFT commute with all the operators of the right CFT.
After you evolve them in time,
If you evolve them with the Hamiltonian of the CFT. Okay, but if you come in here, it's something else. And that's kind of part of the point, yeah? So let's first start on the CFT side, and then we'll discuss the bulk side. So on the CFT side, we have a very simple situation. We just have two completely decoupled CFT. The Hilbert space is factorized. The Hamiltonian is just the sum. So operators on the left commute with ones on the right. They evolve them with this Hamiltonian. Nothing gets mixed together. Yeah, so it's completely separated. But of course, we can consider a state like the TFD state, and that's fine. Obviously, in this state, there will be left-right correlations. But we would not normally think that, an observer from the left can ever interact with an observer from the right. Whereas in this Penrose diagram, clearly they can't. So that's kind of the puzzle of the observer's reality in this situation. But just to emphasize it even more, I mean, if we have a factorized state, then clearly the dual must just be whatever is the ADS dual of this state, and then the ADS dual of that state, and they have no relationship. They cannot be connected, so we'll draw, maybe it's like one of these bag of gold type situations on the left, and a similar bag of gold type of state on the right, or whatever this state is. I mean, it doesn't have to be this state, this is just an example. Okay? But in any case, there's no connection between the left and the right halves in this kind of state. And so
in that picture, could you say what the boundary is?
This, well, this is supposed to be the ADS boundary, the solid line here and here. And then this is, the origin of polar coordinates in the middle. Maybe this is just an example of a factorized, of a pure state. It's like one of these pure states I talked about in the third lecture, where we have an initial value, the evolution of an initial value slice that looks similar to a black hole formed from kilometers. But we could imagine something else. Whatever is the microstructure deep behind the horizon, that's probably a typical microstate, just like that. This is just a cartoon. But the important thing in this cartoon is that the left and right are not connected. And that seems like to fall from logic. The two things have nothing to do with each other. So we immediately notice something peculiar, which is a property of the bulk, like the connectivity of the bulk, does not appear to, cannot be a linear operator on the Hilbert space if we say that this picture is correct and this picture is also correct. Because for any factorized state, we'll say the bulk is never connected. On the other hand, for at least this state, we'll say the bulk is connected, but this state is a linear combination of these states. So if the property is a linear property, you cannot have a linear operator which is zero, not connected on a collection of states, and then somehow non-zero on the sum. That's not possible. In fact, we could make it even worse by noting that if we take states like the TFD state and we evolve them in time or act with other operators on them, they would still be connected. So there's not just one state, one entangled state that we will associate to connected geometries. In a way, by things like the HRT formula, we would associate a connected geometry to almost any highly entangled state, because the entanglement is, well, I mean, especially if we took states where we just evolve, we could just evolve with the Hamiltonian for a very long time on one boundary. That's very similar to the state. It just seems like we cut the state at a different time. Or we might act on this state with things that throw in some shocks, so that we will remain in this connected picture. There are a very large number of states here that seem connected. And on the other hand, all of these states are disconnected and they're clearly not linearly independent collections. So, yeah.
So Daniel, suppose that you take a region in the conformal figure, you compute the entanglement entropy, then using, I don't know what to say, whatever. So what do you want to do? You want to take contribution from both left-handed side and right-handed side? I don't understand how do you get entanglement entropy for this thermal
I meant the entanglement entropy between the whole left with the whole right. So in other words, associated to this factorization of the Hilbert space. So in other words, if I say I trace over the right, and then if I have a state which is entangled between left and right, I have a non-trivial, I have a mixed state on the left, which has some von Neumann entropy. That's the entanglement entropy I was talking about. That could be realized by, in a picture like this, some QFT entanglement between the two sides, or very often realized by some geometric connection, as in this picture where we have a non-trivial, RT surface whose area is non-zero.
And it's always totally symmetric between the left and right?
Well, if we have a pure state of the total system, of course the entanglement entropy from the left and right are equal. It's standard zero.
What do you mean pure? I'm taking, I want to compute the entanglement entropy in the conformal theory. It's necessary, not the pure state. So what does it mean in terms of the left and right?
Well, maybe you're talking about entanglement entropy as a sub-region of one of these CFTs, but that's not what I have discussed.
I have only one CFT. I don't have the.
Here I have two CFTs, so one here and one over here.
In the real physics, there is conformal field theory which is equal to a bound theory, right? So,
Okay.
what exactly are the rules?
Well, I'm not sure if I understand the question completely,
I have any
but
24 super wheels and I want to calculate the entanglement entropy.
well, here I'm doing something different. I have two copies of n equals 4 superior nulls. So I have two decoupled copies of n equals 4 superior nulls, and I'm discussing the alias dual of states of two copies of n equals 4 superior nulls. On the one hand, if I had a factorized state, which is this pure state of one copy of n equals 4, and this other pure state of another copy of n equals 4, then the dual is just whatever is the dual of that and the dual of that. And the entanglement between the left and right copies of n equals 4 is zero because it's factorized. Or I could consider something like the thermofield double state in its two copies of n equals 4. Then we'll say that the dual is the eternal alias 5 Schwarzschild geometry. And then there's a non-trivial, non-zero entanglement entropy between this copy and that copy of n equals 4. I mean,
I guess
we could discuss other situations.
CFT1
we could.
is not CFT2 and there's some geometry maybe.
Yes, right. We could discuss many different setups. This was an easy one to illustrate the point. I mean, a related example that's maybe along the lines that you're saying, although I don't think it will make things less clear for what I want to say, but is if we take a single CFT on the cylinder, and we look at the sort of left half and the right half. Well, now the thing that we usually call the global Hamiltonian couples the left and right. So they're not decoupled dynamically, but we could consider this thing with in the evolution given by the sum of the two Rindler Hamiltonians, which is not something we typically do. Not the difference, but the sum. Okay, so we could consider some H tilde given by, let's call it K, the Rindler generator on the left and right. And then it will look factorized, whereas the global Hamiltonian couples the field, right? There's interaction across the cut. But if we consider, empty ADS in this slice, then this, regardless of what Hamiltonian we say there is, the state looks entangled between the left and right. In fact, it looks like the TFT state with respect to this Hamiltonian, the Rindler-like Hamiltonian. And it's dual to the empty ADS. So this is one of the reasons why we believe that this picture is true, because if the vacuum state is dual of this setup is dual to empty ADS, then we can interpret the vacuum state in evolution under this Rindler-like Hamiltonian, and then it will look like the two-sided planar black hole, right? So this is kind of an evidence of that. It says that you believe ordinary ADS-CFT in the vacuum, you should believe that story too. But here we usually consider evolving in the global Hamiltonian, which mixes the left and right, and that will make, so, okay, that's a different story.
So I'm sorry, I want to, if I start from the low picture, so I start from that state down there. So if I understand correctly, initial assumption that you have is you talk about the theory that this particular state is dual to something that can be described by black hole picture. That's
Okay.
an assumption, right, that you begin with.
Okay, well, I'm not assuming that this state is dual to a black hole, but there's a dual to something. And
But you
doesn't,
no,
this picture I drew a black hole, but that's actually relevant to the point. I'm just trying to be more specific, but the point is that this state is dual to something which is factorized. So in other words, this is a state of the left theory, and this is a state of the right theory. The left and right theory have nothing to do with each other, so whether this is dual to a black hole or a bowling ball, it's still factorized. So this could be a bowling ball in the middle of one ADS, and this could be a black hole in the middle of the other ADS. Or the geometries will not be connected because the state is factorized. That's the only point.
have any geometrical description.
Okay, that's fine too, but in any case, it's not connected to the other one. Okay,
No.
that was the main point, whereas in this state it is, and so the connectivity is not the linear property of the state.
No, why do you compare them?
Because they're two states of the same theory.
Not identical necessarily. And so,
There
by
are
the
two
way,
distinct states of the
there
same
are
theory, but
examples where you have the low-lying state, but you don't have the above state. There are examples in string theory where you have
So-
CFD dual, but you don't have black holes. There are not
So-
states in your theory.
The above
So-
state is
so-
the narrow combination of
so-
the state.
right. So I mean, maybe I should write this
Why not?
formula.
Because it's a linear combination of those.
Maybe I should write
You
this
can only
formula.
define the
Okay.
linear combination of states.
So that's the definition of the TFD state. And so this state is the top picture, and this state is the summand here is a state of this type. So these states must be not connected, and this one is connected. So it says that connected is equal to sum of not connected. Okay, that's the point. So that's the definition of a TFD state.
Linearity of connection.
Right. So connectivity of the dual is not a linear property of this state. I think that's clear in this discussion. Okay. That was all I wanted to say there. Didn't want to say anything very specific about any of these states.
Sorry, can I move on?
But go ahead.
And you don't know that each term in the sum has a interpretation on its own. Perhaps the trick is that here you assume that this specific state has a geometric interpretation. And
Well, if we, yeah.
while actually only the sum has.
Well, okay. So maybe you suggest ADS-CFT is not a duality, but rather that there are some states of the CFT to which you can associate geometries, and then the rest of the states have no interpretation in the dual whatsoever. They're not superpositions of geometries or string or brane configurations. They're simply banned from the discussion. Then, okay, maybe you could accommodate it. Then you have to check something about the numbers of the states which have known duals and compare. And that depends a little bit on if you think that if I take a geometric state and I evolve it in time, it stays geometric, which sounds very likely because, you know, the way you evolve in time in this picture is you just put the time cut at a different point. So if we kind of accept the space-time picture, that would seem to be true. Then you get too many states with clear interpretations on both sides, and you clearly violate linearity. The point is that there are many states whose duals we know very explicitly. It's already too many. It's already too many. But also, I think it would be extremely strange to suggest that that there is not a basis of black hole microstates with geometric duals. but where by geometric, I don't mean some smooth solution of the Einstein equation. I mean describable in the full string theory. Okay, so if we think that we cannot describe in the full string theory a basis of states, it means that string theory is not a theory, right? It's no sense. Anyway, so okay, so there's some assumption here, but it's I think pretty
Can you
mild.
define what you mean by connectivity to full string theory?
Well, yeah, that's maybe a slightly subtle definition, of course. I mean, that could be a subtle thing.
It's
But-
just to define which things are disconnected.
Right,
So that's
right.
easy.
Yeah, disconnected is easy because it's something which the two things have absolutely nothing to do with each other. That seems to have a clear meaning. But connected seems more subtle, right? We could imagine, you know, if we say that it's connected by a string scale tube, then
Geometry
Yeah.
seems more subtle.
geometry is more subtle. But, okay, so that's one aspect, and then, but even in this picture itself, it's already kind of surprising to say that we can throw, if we think from the point of view of an observer in the bulk, there's a surprising thing just in this picture, which is if I send in an observer on a spaceship from this side, and an observer in a spaceship from the other side, they somehow meet in this region. Okay, so, and that meeting is something that sounds extraordinarily strange from the point of view of the dual theory, right? We construct an observer out of left degrees of freedom, we might think. We construct another observer out of right degrees of freedom. We throw in this observer from the two sides, and then they evolve according to the bulk evolution. You know, the evolution which takes you from here to here is not very obvious what it means in the CFT, right? It's some proper time along this observer's world line. What is exactly the dual of that? But then in this space-time diagram, they meet in here. And of course, if this meeting could be communicated to the outside, it will be legal. It will say that you actually have causal propagation from one CFT to the other, which is not consistent with saying the Hamiltonian is this. But somehow it looks like in the bulk something illegal happens. Where illegal here means that it looks, outside of the standard rules of quantum mechanics. So there is something I think very, very surprising about these pictures, and it seems important to understand what it means from the point of view of the observer in the bulk. Now, we might think maybe this is so strange that we don't even believe the picture. Of course, we have so much evidence for it. It's very hard to not believe it. But can we make the meeting in the interior more operational, right? So is there something you could do where you change the story a little bit so that you do see that this meeting takes place? And well, one situation in which that happens is this one, right? Because if we take this, here are the two wedges. If we send something in from the left, oops, and another observer in from the right, and they meet in this region that's behind the Rindler horizons. Of course, if we look at the evolution in the global Hamiltonian, we can pick that spot out again, right? And after all, this is just a particular slicing of the vacuum in global ADS, so it will be pretty surprising to say that this meeting does not take place if we think about the global Hamiltonian. But after all, the global Hamiltonian is just the evolution on not, a different integral of the stress tensor along these two slices, together with the crucial thing that couples the two of them on the two sides. Okay, it's supposed to be the Rindler, the modular Hamiltonian, or in this case, it's just the Rindler generator. So it's in this case, it's just the integral of the stress tensor with different function. And right, so on the other hand, in H global, we see the meeting from the boundary. In other words, you can send the signal back to the boundary that the meeting took place. And it's crucial that in H global, there's a coupling between the left and the right. If you use the global Hamiltonian in this slice and in that slice, but somehow not the thing that coupled them, it's a little bit singular here. But we could imagine that the dual is like a lattice system, that looks like, n equals 4 in the IR, and then we can simply take the global Hamiltonian along two sections of the lattice, but not the hopping terms which connect them. And what will that do? Well, that will cause some shock to go in from those points, and that will prevent this meeting from ever reaching the two boundaries. So the fact that you connect them is crucial.
If you regularize it, you say, take a limit, then you're producing hot waves.
Well, what I mean is, if instead of using the usual global Hamiltonian, so the space looks like a circle, we could evolve it in the global Hamiltonian. There's just a vacuum under the global evolution, and we'll see this meeting. But instead, we could take two sections like this that are where we cut them apart. Then we have to put a boundary condition here. Okay, that's the continuum language. We cut them with a little boundary condition, then we evolve it, and so we have global Hamiltonian on each section, and then appropriate some boundary condition there. And we take the evolution in that. Then we will never see the meeting, because we better not, right? Otherwise, we illegally sent the signal. And the way it works in the bulk is that the evolution in this Hamiltonian with these two boundary conditions throws stuff into the bulk from the place where we put the cut. And that makes the geometry stay have the same Penrose sort of causal structure as the Rindler black hole rather than the global area.
But where did the shockwave come from?
Because I made this cut.
Why is it a shockwave and not something else?
Well, from the point of view of the continuum theory, making a cut injects some high energy, right? So, in other words, the point is that the state is supposed to be the vacuum state of the global Hamiltonian, not a nice state of the system with the boundary condition. It's basically for the same reason that in the continuum QFT, the entanglement entropy is divergent, as UV divergences. So, any nice state in the continuum, any state, including the vacuum, has really infinite amount of entanglement very close to the edge, and because I'm cutting that, it throws in a very high energy thing. But okay, so.
The shockwaves are property of the bulk. What is the boundary picture of them?
The boundary picture is just, the point here is that from the boundary point of view, it's obvious that you will not be able to send the signal from the left to right if I evolve in the Hamiltonian, which doesn't couple them. That's completely obvious, but it looks not so obvious in the bulk. And in specific examples, if you cut it in some way, then you will get shock waves in the bulk, which make the bulk return the same answer. Now, you can try to find a way to cut it, which does not produce the shock, but then if you succeed, you'll drive a contradiction, so it's not very likely that that will succeed. But okay. It's like,
What kind of boundary conditions?
Well, the simplest thing we could imagine is, some kind of Neumann type boundary condition. Like if I had a lattice and I just stopped the lattice. Yeah. So just any boundary condition has to reflect the energy. It's related, except it's a very extreme defect which just cuts the boundary in half. Right?
Yeah, and there have to be two.
Right, one here and one here. It's a boundary condition. Yeah. Okay, so, and now there's an analog of this story in this two-sided case where each CFT was on a full global slice, and that's so then that picture is the natural one, or the initial one, but now we can try to couple the two CFTs to get more like this picture, so that we can operationally detect this somewhat mysterious meeting in the interior. And so then so now we go back to forget this Rindler discussion, and we go back to the thing we had two CFTs. So you have CFT left plus CFT right, and now we put in an interaction, maybe some coupling, integral over the space-time of the CFT, some left operator times some right operator. And now they don't have to be the same operator, but this is the sort of simplest example. Okay? And we may take this coupling, actually maybe I'll put, oh, that was a mistake. I'll put the coupling in here because we might take the coupling to be time dependent in general. So we can consider different situations. We can have a thing where we leave the coupling on constant for all time, or we could start with them factorized, couple them, and then decouple them, and they have somewhat different physics, and I'll discuss all. So
And this formula, OL is localized
OL is a local operator
on the left.
on the left, and O right is a local, the same operator
Why
on
is
the right.
that?
Yeah.
If they're localized in destroyed regions, why is it zero?
This might be zero.
Well, OL,
Okay, I see. I mean, I'm using X to parameterize the coordinate in both of them.
yeah.
Okay, so what I mean is, let's say this one, it's like a bilayer system, okay? Here's CFT left, and here's CFT right. And
There's some
And this
point-
is the X plane, and this I'm not describing, okay? So we could say X left and X right. X left, X right, they have the same X coordinate, but one of them is in the left CFT and the other is in the right CFT. Is that clarified? Yeah? Yeah?
An example maybe clarifying thing to me, so suppose the CFT2 that you have in mind is CFT2 dual to string theory and ADS3.
Okay, yeah.
What is, can you describe the thing that you are doing now in that language of string theory and ADS3? What are you doing?
Right, so I have two asymptotically, because I didn't tell you a state, I'm not telling you yet a whole geometry, but I have to just describe the asymptotic problem. So we have, originally we had a pair of asymptotically ADS3. Depending on the state, the geometries might be connected, not connected, something else, whatever. That's not part of the definition of the Hamiltonian. And then we add a coupling, which directly couples the two boundaries point by point.
I guess what's confusing, so top, you wrote DDX. Part of that is.
Part of that is time, yeah.
T is common to both.
T is common to both, and X is common
But
to both.
X, but a local operator is a smeared thing over a region of X. It's not a point, it's not a delta function. To define it carefully, you need some kind of smearing.
No, I meant this, but we could also consider something else, which is like more non-local.
But I guess, but those 2 points are only identified at one point.
Yeah.
So what is the integral over X mean? The delta function?
Well, maybe, let me draw a different picture, maybe we'll make it clearer. Let's suppose that instead of a CFT, I have a lattice system, a spin chain. Okay, so let's say that's CFT left and right are both spin chains. So here are the lattice sides, I'm only going to draw space. Here are the lattice sides of the left guy, and here are the lattice sides of the right guy. And then in the original theory, there are couplings, along links in each of them. So this is H left and this is H right. And now this interaction, it looks like adding some links like this. And then by this direction is X. And then there's also time, and it's local in time.
Okay, so you're actually adding some kind of local, which isn't shrunk to a point.
Shrunk to a point.
It's not just one lattice side.
Not just one lattice side, all of them, yeah. This is what we did in the original paper. We could consider different kind of couplings. The effects will be slightly different. But. So with a coupling like this, it has the same Poincare symmetries as the original CFT. The break conformal symmetry, but it has kind of d-dimensional Poincare variance. Right, but it even breaks all the conformal symmetry. So yeah, but it breaks 2 copies of Poincare invariance to 1 copy of Poincare invariance. If we did something more arbitrary that looks kind of more non-local-ish in that language, maybe break it more or whatever. So one can consider this kind of coupling, and if we, so now we can have a few different discussions. So if we started in the TFD state, and then we turn this coupling on and off, maybe we act with it instantaneously, or we turn it on and off in a short window. That's what. Then the geometry looks like. Then the ADS stool looks like this. So originally, we have the TFD states, the eternal black hole. We're evolving it into decoupled Hamiltonian, so it's just the standard eternal black hole. But then there's this time window, let's say at around t = 0, where we turn on the interaction. So this is associated to this coupling localized in time. And when you do that, what does this do? This changes the boundary. So this is a double trace interaction, right? It's a single trace times single trace in the language of large gauge theory. Just to remind you, if I added a term with a single trace, that's like a source, so it sends in a classical, turns on a classical value. If I turn on the coupling by a finite amount, it will put it in a coherent state, at least to leading order. Here, it's putting in a squeeze state, because it's something which is quadratic in the field operator. So if I act with, so when I add this to the Hamiltonian, I act with exponential I alpha of the coefficient mu, which is the coefficient, some O left, O right, act with this kind of operator. This is something exponential of quadratic in the field, that creates squeeze states. Whereas something like that creates coherent states. And we're working in the quadratic approximation of the field here. Sorry?
Squeeze states in this direct problem.
Squeeze states in the bulk.
In the bulk,
Yeah.
actually.
And the bulk is not, the bulk Hilbert space does not look factorized, right? So if we just say, at the level of just studying QFT in a fixed bulk background, we just have this one connected space-time, we quantize fields in it. It's not really factorized because of some bulk QFT UV issues, or, it's not naturally factorized. Right? But anyway, so this adds in some kind of squeeze state, and in states like this, the expectation value of the stress energy tensor is generated at linear order in the coefficient. If we have coherent states, the expectation value of the stress tensor is quadratic, right? So in other words, if we have classical field configurations, the expression for the energy density is quadratic in the field. Simple effect of electromagnetism or scalar field theory. But if I have, so therefore if I have a coherent state, e to the I some operator, then the expectation value of any components of the stress tensor has to start quadratic in alpha, assuming that the original background had this field turned on, okay? Then there will not be any linear term, and because of this, it's possible that there are energy conditions which say that some expectation value of certain components or integrals of certain components can have a definite sign. The most famous of which is the average null energy condition, that the integral of null component of the stress energy tensor along the null line has to be positive. That makes sense because of this fact, okay? Because it starts with quadratic. But here we added this double trace interaction. We produced a squeeze state. The expectation value of the stress tensor in this kind of state, remember the stress tensor is quadratic. We do the computation in the bulk. This is the bulk stress energy tensor. The stress tensor of quantum field theories that lives in the bulk. The bulk, imagine that the bulk field is, a free field, good leading approximation, okay? The stress tensor will be quadratic in the field. This is quadratic in the field, and so this thing will be linear in mu. So this something linear in mu, and so therefore it cannot have any sign property. Because if I flip the sign of mu, I flip the sign of this. And in this picture, it's compatible with the theorem of the ANAC, because the ANAC applies to, for example, this null line, but this coupling violates one of the assumptions of the proofs of the ANAC, which is that the traversing line is the fastest path between these 2 points. But now it's not the fastest path because there is a direct coupling between left and right here. So that violates the assumptions of proof of the ANAC, and therefore it does not apply. And indeed, with this kind of interaction, one can get a negative null energy along this line. Okay? So everything is consistent. Okay, so for
And if you didn't, you could just change the sign of
exactly. So for appropriate sign of mu, the integral of the expectation value of the average null energy along that line is less than 0. And in gravity coupled to matter, the thing which normally prevents traversable wormholes is the average null energy condition. So one can show that if you have a traversable wormhole, then the integral of the null energy along a traversing null path has to be negative. Okay. I mean, heuristically, this follows from the Red-Chuduri equation. There's a kind of, on one side of the wormhole, there's always a net, there's a convergence of null rays that enter the wormhole, and in order to get out, they have to diverge, and that requires the negative null source. But here we get it, so it works, but there's no inconsistency with causality because we put this direct coupling. Okay. In a certain sense, the example of Adius-Rindler we could think of in the same language. Okay. We just don't usually, because we just take the global picture and it seems trivial that we get connected geometry.
It shows that there could exist coupling between these two systems which have traversable wormhole. There could also exist coupling that don't, right?
Yes, of course. Yeah. Of course, yeah. So it's allowed, but very simple couplings, if we start with the TFT state, do the job. Okay, so one does get this sign, and it works. Now, so this gives a way to, in a way, operationalize the picture where this mysterious meeting behind the horizon takes place. You can turn on this coupling, and now you can send a signal. Now you can see at the boundary that the meeting took place. Okay, so I think that's an interesting point. And this particular setup where we turn the coupling on only for a short period and then turn it off, we can ask, what does this whole story look like from the boundary point of view? And from the boundary point of view, it looks like a form of quantum teleportation. Because if we send the signal through, so after we take into account the back reaction, now we get a Penrose diagram that's elongated. Okay, a kind of elongated Penrose diagram. And now there are paths that reach from left to right. And this wormhole is only open for some finite amount of time. Now, of course, because this effect is quantum, one loop effect, this time is very short, right? It's some like Planckian time. So the wormhole is not open very long, but it's not that hard to get through because of the geometry of the black hole. There's a large range of times on the boundary which all focus to near the bifurcate point of the original spacetime, and so they can fit through this narrow time window. But that does present a limitation on how much you can send through. If you send in something very heavy, then it will have its own back reaction and will not end up traversing. Okay, so, but that can be made quantitative in specific scenarios. But anyway, if we look at a situation where something does get through, then we can say, what is the boundary interpretation of this signal reaching the other boundary? and it looks like a form of quantum teleportation. We can imagine that the traversing particle carries a particular quantum state, say some qubit Q, and then we started with an entangled state. We throw in this qubit. We evolve in the boundary time for a while. Then we do this left-right interaction. Then we evolve in boundary time some more, and we read the qubit out on the other side. And the interaction has this form. But this kind of interaction we could also equally well have interpreted as, it doesn't matter whether we think of this as a quantum channel or a classical channel, in the sense that if you measured O left, and simply acted on the right with the unitary operator given by this expression where I put here whatever I measured as O left, from the point of view of the right, that is absolutely identical. So we could say it another way. Suppose we act with this quantum operator, and then we measure O left just afterward.
Putting in the mathematical expression projection on the
Right, so we can write it like this. E to the I mu O left, O right is equal to integral over lambda, where lambda is a possible eigenvalue of O left, of e to the I mu lambda O right, delta of O left minus lambda. In other words, the projector that we get lambda. If O has a discrete spectrum, we replace that by a sum, and this is the projector. So this is just a trivial mathematical identity.
This is the process of teleportation. If someone is a state Q on one side and that on the other side.
Exactly. So if we implement this coupling in this way, it's standard. It's a form of standard teleportation, in that you start with an entangled state and the qubit on the left. You do some unitary operation purely on the left. You make a measurement on the left, and then I do some unitary on the right, and I get out the qubit on the right. So that's the kind of abstract structure of teleportation. Of course, it's a very special kind of teleportation that has this dual. It's some, if this was this system here was a lattice system or something, it's some kind of many-body teleportation. Any question?
With your teleportation, you don't send the particle, but only the information about the quantum state. But here, if you throw a stone, you will not come to the other.
Well, that's a very interesting question. So we could say, if this is made of real black holes, then we throw a stone, we get out a stone. Okay, but maybe we could say it in a different way. Suppose you wanted to teleport a stone. Okay, well, or a person. Normally, what we might do is, instead of trying to send the full information of a stone for the person, we will, write, okay, it's kind of like a round stone with a few features, and we just send that. And then the other guy tries to build a similar stone. Then we're just sending some simple information. There's a compression step. Okay? But we could try to send the full information of the stone or a person. And what does that really mean? Well, it means we look at the volume of, so here's the stone, and now we look at a volume of space-time around the stone, and we say, well, from the point of view of the fundamental theory, we want to send the full state, the full information in the fundamental theory contained in this region of space. Okay, now that's a huge amount of information, right? It's the total possible number of states in this region is given by the Bekenstein-Hawking formula, roughly, with something of this area. And so we need an enormous reservoir of entanglement. So what do? Well, we take our entangled state can be the maximally entangled state between this chunk of space and another chunk of space of the same size. So here's the region on this side, here's the region on the left, here's the right, here's the left. If I take the maximally entangled state of these two regions of space, that is the actual Einstein-Rosen bridge. Okay. Now we start with a non-traversable wormhole. Now we have our stone, and now we can send the full information of the stone in the exact theory. Well, how do we do it? Well, we throw it in here, and it looks like it gets stuck. And it better get stuck at first, right? Because there's not yet any interaction. We cannot send it to, across the galaxy without any other signal. We need the other part of the teleportation protocol, which is we make some measurements near here, we send it to the other side, and then suddenly the stone comes out. But if we do it like this, the stone has its own story. It says it went through this tunnel in space-time. It has a kind of causal history to get to the other side. So I think that's actually one of the deepest aspects of this business. It kind of says that at least for certain kinds of teleportation protocols, there's like a causal explanation from the point of view of the thing being sent, where it feels like it went through, it went through the wormhole, and it has a causal history that connects it, starting on its initial, starting where it was sent in until where it comes out. But that's very different than the usual picture of teleportation. It sounds more like you destroyed the qubit on one side and somehow you replicate the information on the other side.
But you have to show first some EPR pair, right?
Yeah, well, here the shared EPR pair is the Einstein-Rosen bridge. So it's the two entangled black holes, which, as we said, is supposed to be the CR bridge. Well, I think that's probably a hint of something, but I'm not totally sure what the something is. But, so what we might say, this is like, the gravity picture is like the description of quantum teleportation from the point of view of the qubit being sent. Now, if we talk about standard simple teleportation, there's not much of a wormhole picture. It's just an EPR pair. We don't learn very much. It's a Planckian wormhole who has no definition that we know of. But if we, if the left and right system here are some lattice system that looks in the IR like n equals 4 super Yang-Mills, then it's pretty good, okay? And, actually it's kind of curious, like if somebody made material like that, which was say a lattice system that in the IR looked like a large N gauge theory. Let's say that the lattice system had a conserved current, interacted with photons of the real world. Well, what happens if you will shine light on this kind of setup? Well, the light will come out the other side, and it will come out the other side in exactly the way it would if it went through, So, somewhat in the same way.
What do you mean by, you're trying to see how you would see in the middle of the transversibility
Right.
of the wormhole. So what would be the...
Well, what you mean like when it's here? Yeah, when it's here, it's somehow more delocalized from the point of view of the boundary system. So it looks like what has happened is that let's say we go back to the case we threw in one qubit, this qubit is now encoded in a product over many operators, and maybe I'll describe that a little bit right now. Yeah.
So did you explain the paradox here of the two people meeting? Is it related?
Well, I would say this is a way, this kind of protocol is a way to, really, drives home the point that this meeting indeed takes place.
The space is really connected.
It's really connected. Right?
So who turned on this interaction?
Well, so the point is, well, okay, of course we can never, if we say that if we declare that we are not going to enter the bulk, we will only make measurements on the boundary, then we can never prove anything absolutely about the bulk, because all we can do is say that we make some measurements at the boundary and make some observations at the boundary. but we kind
Here.
of construct the bulk in our heads, right?
And that bulk, even before you throw it and do anything, it is somehow connected at this point.
Right, so, I mean, I think we would like to say that this is the space-time diagram regardless of whether we turn on another coupling by sort of causality or something, and we cannot have produced the interior by turning on the coupling.
Daniel, so
Oh, yeah, go
it
ahead.
could be very, very primitive. Let's say, yes, here is, I succeeded to construct an equal four. This is my iPhone.
Yes.
And I take another iPhone, and I look at the picture you just covered.
Oh, yeah.
Because now there's going to be a coupling between these two iPhones.
Okay.
There is no ADS in between, it's flat space, okay? But that's, you force me by this coupling to say there is an extra dimension, and that extra dimension doesn't sit in ADS.
No, the extra dimension exists, whether,
Here it, well,
well, the extra dimension can be constructed without the other side.
Right. Right, I mean, it's not, it's
but
like a
not
Randall
ADS.
syndrome.
Is it ADS too, I mean ADS, so is it some ADS? Because you need ADS for this game, at this stage. So
Right, right. Okay, I think I understand. I mean, oops. I mean, maybe we can discuss the following situation. We could discuss a situation which is very clear, and then there are ones where, okay. So, I mean, let's suppose we had, the Einstein-Hilbert action in 4 dimensions, plus, the metric coupled to n equals 4 super Yang-Mills. Okay, I'm just drawing the Yang-Mills term, but you can imagine the rest. So I have n equals 4 super Yang-Mills, SUN, coupled to gravity, together with the ordinary Einstein-Hilbert action in 4D. Okay. Now, what is the dual of this? Well, this is a Randall syndrome type of brain world, right? We have the emergent direction of ADS, or we might call it Z direction, but instead of it going all the way out to a rigid boundary at Z equals 0, as it would if the metric was fixed, instead that metric is dynamical, and so there's a UV brain where the metric fluctuates. The 4D metric. So this is 4D, this is one extra, and this metric fluctuates, and so the Einstein-Hilbert term is about the fluctuations of this brain, and then there's also this extra direction of ADS. Okay, so here that would be completely clear that if we had, a brain world scenario of this type with a fifth dimension, it will be could be, some particular setup like this, exactly equivalent to this Lagrangian and so on. Oh, we can ask whether this thing is UV complete and so on. Okay, so put that aside. Now we could discuss different kinds. So okay, so I mean this in this example, if we live here and we discuss 2 entangled glue balls, they will be dual to a thing that looks like a tunnel here, right? I mean, so here it's kind of completely clear, right? Now, if we go a little further, we might say, I'm trying to connect to the iPhone. Okay. So we don't have this in the fundamental Lagrangian, right? But we might have a material in your iPhone which at low energies looks like this. So we have we have an iPhone. Which gives this in the IR, okay? Well, but when we say that, that's not precisely right, because it will not be something with the speed of light. in the material in your iPhone is the speed of light in a vacuum, right? So it's not going to be exactly this Lagrangian. It's going to be modulated. And there will be other components of the stress energy tensor in your iPhone. It will be something like fluid Lagrangian, where it looks like this in the co-moving frame of the fluid, but there is an embedding between the fluid coordinates and the space-time coordinates, right? So there'll be some material map of like x mu into some f of some fluid embedding map. Let me write this very clearly. So, from the point of view of the effective description in the material, there will be some elements, x, and they will map to f of x in space-time. And this thing will be modulated by this in the sense that we have to map the metric with, including derivatives of this function, right? There'll be factors that look like d mu of f. Multiplying the metric there, so it's like the induced metric in the material, and that's the thing that tells you that the speed of light is not the same as in the vacuum. Okay? And then there will presumably be other components of the stress energy tensor, so there'll be other terms here. But that's still a kind of brain world-like scenario. It's slightly more complicated boundary condition, slightly more complicated action on this brain from the point of view of the bulk. And at very short distance, it looks much uglier, right? At short distance, you see the underlying lattice of this material. So the space is kind of turns into spaghetti or something. But if we look at long wavelength modes, it will see an effective action of this type, again modulated by this some embedding function that fixes the speed of light. So in that story, you now take your chunk. So this one line represents our 3D space. And then over here, you have two chunks of this special material. Well, each of them on its own, it has an extra dimension, the z direction, which kind of dangles off. Again, if we were in this case, we would have drawn this extra dimension everywhere. It will be like a Rambo-Sundrum scenario, but here we only have it in some defined regions. And the boundary condition here of the brain is a little more complicated again because of this feature. And at very short distance, it looks much more complicated, but if we look at long wavelength. And then we put these into an entangled state, and we get something that looks like, a two-sided black hole in this geometry. So in this third direction, if we look across it, we have a picture that looks like, if we take this direction plus time, that looks like the usual Adias-Schwarzschild kind of Penrose diagram. But again, the boundaries are complicated because they glue to this thing. And then if we, you can shine some photons onto this material, they couple to some charged operator in this theory. In the dual picture, they fall into the interior as a photon of the dual theory, and they can pass through this if we include this kind of interaction. You read them out over here. That's sort of the setup. Is that answer the question?
Sorry.
Half an hour.
Oh, okay.
Why can we interpret an iPhone as a random Sundrum plane?
Sorry, one second. Could you say again?
Why we can interpret an iPhone as a random Sundrum plane?
Well, the point was Eliezer had a very special iPhone which had in it a material that at long distances looked like n equals 4 super-Young melons. So I don't know where he got this iPhone. It's from the future. Now, okay, let's see. So given the time, what I actually want to tell you about, well, okay, we got a blank spot here. So we'll cover this, sorry. One version of this, which is very clean, is when the boundary system is just the quantum mechanics, and the bulk is ADS2, and that comes when you have two coupled SYK models. So instead of taking two coupled CFTs, we can take SYK left plus SYK right. These are have to be the same instantiation of SYK, because remember, SYK has this couplings of 4 Majoranas with some random couplings. But we take the J's to be here and here the same set of J's. That's very important. Then we can discuss the TFD state in this geometry, in this theory, and we'll associate it to the two-sided black hole with nearly ADS2 boundary conditions. And of course, here the bulk theory is more complicated, is some particular theory. We don't have actually full understanding of the bulk theory. But at sort of leading order, it looks like JT gravity. And then there are the individual Majoranas, of which we have n species, 4 indices from 1 to n. So there are basically n fermionic fields also living in this bulk. And they have other interactions that are not just gravitational, but in some limits, the gravitational scattering dominates. So we can take this system, and then we can play the same game here. So we turn on a coupling. Now we can take the coupling to look like this. Local in time, of course. But we add this term to the Hamiltonian. With some coefficient, like pi or whatever. Now, in this case, because these are fermions, this cannot be reinterpreted as standard teleportation. We might call it fermionic teleportation. In any case, it's a quantum interaction. If we modified this a little bit, we could have taken a product of 2 Majoranas on each side, then that would be a bosonic operator. We could use the other language. But the physics in the bulk doesn't care very much. From the point of view of the bulk physics, that's a detail. When you turn on this interaction, there's a very simple way of seeing how everything works in this geometry. First, the kind of semi-classical picture that I described can be reinterpreted in a very simple way here, which is that when I turn on the left-right interaction, it gives a kick to the boundary. So the leading effect of the 2D JT gravity is just about the boundary, like the position of the boundary. On shell, there are only 3 solutions. So there's a sort of off-shell action, which is given by the Schwartzian, but the classical solutions of the Schwartzian just parameterized by SL2R. So when there's a kick, we just kind of get some. It's very simple, and typically, if you throw in typical kind of thing that I would act with on this point will insert positive energy and it will kick the boundary out. But with this interaction with the appropriate sign has negative energy and it will kick the boundary in. And so because it kicks the boundary in, we'll go on this trajectory, and now a path like this can get through and reach the other side. So this is a kind of nice place to do these computations. Moreover, because you have n fields, you can turn on this interaction for n of them instead of just 1. And turning it on for n makes this picture more semi-classical, so it makes the time window which this is open in order 1 time instead of some Planckian time, because the ADS radius in Planck units is set by the same n, and the one-loop matter stress energy tensor associated to this kick also come with the same factor of n, so they cancel. There's other situations where you can get that enhancement that makes these wormholes more semi-classical in the bulk picture, even if we started with only 1 field, because what you really need is a large number of fields in the near horizon region. So if we had near extremal magnetic black holes, and there was, in the theory, a single species of massless fermion, they will develop Landau levels, and it will look effectively like many fields in the near horizon region, and it kind of is described by this picture. Malvasena and collaborators had an interesting paper where they discussed a situation like that using the fields of the real world. We don't have any massless fermions at low energies in the standard model, but if you are above the electroweak scale in energy, then the fermion looks massless. So if you had two tiny black holes whose Schwarzschild radius is smaller than the electroweak scale, that's still much bigger than the Planck length, so they're still well described by semi-classical gravity, which were threaded by a large magnetic flux. So now we can't say anymore whether it's U1 or SU2, but anyway, the flux of the magnetic electroweak flux. Then the fermions of the standard model will live in Landau levels, and we'll get exactly this kind of scenario, and the ground state will look like this kind of configuration. So there's some quantitative question of whether if I took two separate such black holes and bring them near each other, do they relax to this ground state that looks like a wormhole faster than they will infall? So that's a quantitative question, but I think that's a very cute fact. But in any case, in the SYK model, it has this sort of especially simple situation, and one can even try to realize these systems in quantum devices. Of course, to realize the larger SYK model is far beyond the current abilities, but the basic properties of this picture persist even to pretty small n, even down to n of order 10, which is somewhat surprising. By the basic properties, what I mean is, if I add this interaction, so there are a number of other, So I said the signal only gets through, the wormhole is only traversable when I put a particular sign of mu. But if I just look at the signal from left to right, there's a non-zero signal even with the wrong sign, especially at late times, which comes for the following reason. So if we look at the T of D state, when we act over here, we have e to the I alpha, whatever is this excitation. I don't know what we'll send through. I don't know, phi. Okay. So phi is the traversing object. So this is the initial state. And then we evolve for a while, and we act with this interaction, e to the I mu, all left, all right, summed or whatever. And then we want to measure out basically phi on the right at later times. And we want to compute, so this is our state eventually, and we want to compute the expectation value phi right in this state. And phi right is at this later time, and phi left is at this earlier time. Just not right away parameters. Now, if I did not, so we can say if I have in this thing the 1, the part where I did not act with it, then I just have this operator acting on the T of D state, and at leading order, I just compute the expectation value of O left, O right, which is some number because it has a thermal correlation. It has the left-right correlation of the T of D state. So I get a phase e to the I mu times something. So I get an e to the I mu thermal O left, O right. Beta is the inverse temperature of the T of D. On the other hand, if I had acted with this, then I'm now computing the t equals 0 left-right correlation function in the state with a kick on the left in the past. And if I have if the system has scrambling, this is basically an out-of-time autocorrelator, and at very late times, this expectation value will be 0. So at leading order, acting with this thing just gives nothing. Okay.
U is very small, and that's why you lifted the expectation value to the exponent?
No, mu is not necessarily very small. It's just that if I have if the expectation value of this is kind of big, then the leading effect is, in other words, if it's kind of the approximation of treating the expectation value of this is like a classical bed. And that's basically because the bulk theory is, if we assume the bulk theory is free up to the coupling to gravity, then we can Taylor expand this formula, and then we have to contract them by Wick contractions. Basically doing that corresponds to summing only the graviton ladder exchange diagrams. Okay, so we'll kind of do a Taylor series expansion, and then each of them just contracts in pairs. And the only thing that couples, so the violation will be if there are non-trivial higher point correlators of O left, O rights, right? But if we assume that those only come from exchange of the JT graviton, then we take that into account by just evaluating it in the state.
Daniel, previously we talked about switching on and then switching off, but now it seems that it's simply the theory with the coupling. That's
I might have said one word like that, but mostly I'm still imagining I switch it on and off. But we'll discuss it with it turned on all the time in a second. Okay, so the point here is that if I didn't have this, I will have this phase to first approximation. If I do have this, I have a trivial phase. And so that gives me a phase difference between the two pieces of this state. Let's say alpha is small. So we have two pieces of this state, the one with 1 and the one with alpha, and they come with two different phases. And so then in the end, I do get a non-zero effect in the expectation value. And this thing has nothing to do with the sign of mu. It just has to do with the fact that this phase is different than that phase. So we can think of this more like a quantum interference effect. It's not associated with causal propagation. And it happens at late times when this correlator kind of gets kicked to 0. From that point of view, the situation when there's a causal signal corresponds to an enhanced peak, kind of an enhancement with the appropriate sign of mu at the correct time scale. Okay, so if one drew a plot of sort of just the left to right signal, it will look something like, it will have some kind of peak near the scrambling time, which is the window for causal propagation, and then it will decay, but not to 0, but to a value given by this. Whereas so this is with the sort of correct sign of the coupling, and with the other sign of the coupling, I'll have something more like that. Okay. So, well, like the signal, like where expectation value means I put in all the other evolutions and so on. So the expectation value of phi right in the state where I defined with all this.
And the other axis is
And the other axis is time. Okay. And the two curves are the two sides of the coupling. So this is roughly the picture, and one can do these computations in the SYK model analytically in large n limit. And there are various generalizations. There's like the Q local version of SYK, and in the limit of large N and large Q, but N much bigger than Q, one can solve this problem analytically, and it reproduces, that's where these curves come from. Well, this is sort of a picture of the plot at infinite N, and yeah.
the separation between them and the signal independent.
No, not if you normalize this mu in the conventional way. Maybe I should have put.
What's the bulk picture of this? So this doesn't have any geometrical interpretation?
The bulk picture is also an interference effect. So the bulk is also quantum mechanical. Yeah. Right. So this late time thing happens in any sufficiently scrambled quantum system. It's a very general phenomenon. It will happen if the evolution here is not this Hamiltonian, but a random Hamiltonian, or a non-random Hamiltonian that has nothing to do with holography and so on. So this is a very general thing. But this peak is more special. And from the microscopic point of view, one can especially in the SYK-like models, one can understand something about that peak in a slightly different language. So so the interaction operator is this thing, but our theory is just a bunch of Majoranas with some Hamiltonian. So what is this operator count? If we have an operator on the left, it will be a general operator on the left is a product of terms with different numbers of Majoranas. So we can write a left operator as sum over, let's say s equals 1 to n of psi to the s, where this has s indices. Okay, so for each s, there are many such terms, and then we have some coefficients here. Sometimes this number s is called the size. So any operator can be written as a product of sum over products of Majoranas, and a given product has a given number of size in it. Of course, there are many operators of each size. Okay? So if we start with this thing, if we forget about the state for a second, we just think about the Heisenberg evolution. We kind of inject the Majorana on the left, we conjugate it by the Hamiltonian, and now it becomes a more complicated operator, which involves product of many size in general. And we can decompose it in this size basis. And in this basis, this coupling acts in a very simple way, because this is just the sum over all of them, and so it just counts the size. Okay? This coupling basically counts the size. Well, we wanted to start in the T of D state.
Starting with the psi left only, what do you mean counts specific?
Right. I started with just the psi left. Yeah. So when I
Those operators in a different exactly on the left time, like space.
right, it's acting. That's right. But what I mean is. If so, let's say I take the infinite temperature T of D state, which maybe I'll call I, because if I write, of course I can write a state in the double Hilbert space as an operator in the single Hilbert space. I start with the infinite temperature T of D state, and I act with some left psi on it, maybe evolved in time by some amount. This is some state of the coupled system, but I can also interpret it as an operator of the original, of just the left system. And then I want to act on this thing with e to the I. Well, let me consider the action on this thing by this operator. The eigenstates of this operator. So if this thing is a product of S Majoranas of the left, then I can pull this around it, picking up exactly S. Okay, so I'm pulling this over here, I get exactly S, and then I would act this thing on the infinite temperature T of D state. It has a trivial action. Okay, so basically this state is an eigenstate of this operator with eigenvalue S, up to some multiplicative. And so this is basically an eigenstate of the thing with eigenvalue S. And now we really wanted the T of D state here, so we do the same thing with the T of D state. We take this whole business and expand it in terms of operators with size S acting on the infinite temperature T of D state with some coefficients. These are basically eigenstates of this operator, and it's very easy to see what happens when you act with this thing in its own eigenvectors. And this peak is associated to situations where the phase of these state, the phase of the state in this eigenbasis, phase of the state in this eigenbasis is linear in S. So in other words, it's like a situation where this state is an eigenstate of the operator conjugate to this operator, but that's not the precise language because the size operator doesn't have a canonical conjugate because the dimensionality of the Hilbert space with different sizes is not the same. Okay? But the property of the state having a size which is linear in S is perfectly well defined. So if the phase of this state in this basis, if all the operators with the same size have the same phase, and the phase is e to the I s times a number alpha, which is this independent of s, that's associated with having that peak. Okay. And so these features persist even to pretty low values of n. To actually implement such things, even n equals 10 syk is too hard because it involves many terms. 10 choose 4 terms in the Hamiltonian, so there's many gate operations. And one needs to find even sparser versions. And even in very sparse versions, one can still find situations where the phases are aligned like this. But there's some price to pay, which is that the number of Majorana strings you generate is not as many. So you have fewer points. You don't generate all Majorana strings, only some, but the ones you generate do align in this way. So it's kind of the most pared down thing which still exhibits this property that is possible to run. But I think these devices get better and it will be possible to do things that are better. I think that's the scenario there. Let's see. So I think that's kind of it for what I wanted to say about these wormholes.
Experiment, the realization is that you guys carried out with Google.
Yeah.
Is more than just an illustration that of machine learning ability to pick out sparse states in this thing. I mean, what is it really? Anything and the ability to pick out sparse can work better than one might have expected.
Well,
Animal, right?
right. I mean, I think one thing we learned is that much smaller and much sparser Hamiltonians can still exhibit this kind of phase, linear phase and phase alignment than we might have realized.
Indeed, two lessons. One is n equals 10, it's close to n equals infinity-ish.
Yeah.
Two, machine learning helps a lot in picking out.
Yeah, that's right. But it could even be that there are, I mean, maybe there are just many Hamiltonians which exhibit this phenomenon. I mean, so.
So one needs machine learning to teach us which Hamiltonians to look at.
Possibly, or that's possible, or we might be able to figure it out too. I mean, yeah.
There were some lessons that you learned from the sparseness lecture. There were some patterns.
Right. I
Is
mean,
there a developed understanding?
I think the. That's not completely clear yet. I mean, there's also a. So it's also known that at large n, random sparsification still analytically preserves the basic properties of SYK. Well, you just randomly select which J's to turn on and which not to turn on. And it turns out, so let's say when we have 4 Majoranas, we have kind of n to the 4 couplings. But if you make a random sparsification with n coupling, or maybe n to the a, n to the 1 plus epsilon couplings turned on is already enough in a large N. So that's even from analytic. Enough so that the leading order correlators, that there's still a Schwarzian mole. So the low temperatures, that's for sufficiently large N. For smaller N, random sparsification is not a good idea because you'll end up making it too disconnected. But it's not completely clear Yeah, yeah. So I think it's still to be understood exactly whether there is sort of some very nice patterns or whether pretty random things will work. And that's to be understood.
The way to learn that would be to increase N.
Yeah, to increase N and to, no, just study more examples. So, okay, so that was that story. I guess maybe I should just stop, although at some point I thought I would talk a little bit about this observer Hamiltonians, but maybe there's not time.
I see for today, for this lecture, we have to, I don't know if we want to add at the end extra time. This is,
But I
at the
think
end of
we're
the day,
we're done.
Well,
No,
running
we're
into
done.
the next speaker, who, that's it.
That's me, by the way.
Yeah. So okay. So I think this is a good stopping point.
Yeah, because
Yeah.
the topic can't do it part.
No, I don't think so.
But
So
we might have the last 3
Well,
minutes for questions.
yeah. So any other questions? Maybe people.
Does it in any way help alleviate this weirdness before you turn on the conflict? You have this classic story, but you say it's kind of weird that things meet in the middle, but you don't see it on the boundary. It's kind of a vague question, but
Right.
the story remains the same, right?
Right. The story remains the same. I mean, I think what this setup says is that if you modify this situation so that you can probe from the boundary, the place in the bulk where something mysterious happened, then when you do that, you've changed the setup at least a little bit, and it always in a way that the results you get in the boundary look consistent with quantum mechanics. But how will we actually calculate the probability that an observer in the bulk measures something when they measure it after some amount of proper evolution? That somehow is not answered by this. But I think these kind of setups strongly constrain the possibilities, because whatever you think is the way to do the bulk computation, it has to ultimately agree with what you measure from the boundary. And these particular kind of setups are very stringent constraints on that, because they seems like depending on what you do, what you want to say the bulk observer measures sort of depends on the state in a rather surprising way, right? And so, I think an ultimate hope here is that by, that somehow by looking at a variety of different boundary setups, we'll sufficiently constrain what the bulk observer must be seeing to be consistent with all of them, that we will be able to learn, what the rules are. That was the kind of what I was going to talk about.
What about learning about the singularity?
Yeah, that's a very interesting question. I mean, this will not, no probe from the boundary will ever directly tell you about that, but
But you get closer.
you get a little closer. Yeah, I don't have anything else to say about the singularity.
Okay, let's thank Daniel again.